Okay. So, so little before we discuss Hongu-Mandel effect and Mach-Zehnder interferometer, we will go over a little mathematical drill. So last time we saw how you can write down a Hamiltonian for the beam filter transformation and solve the Heisenberg equation of motion and see how the mode operators transform. Okay, so the same exercise can also be accomplished through the unitary transformation. So we have these mode operators A and B, which are the which correspond to the input modes of the beam splitter. And they transform as A theta and B theta, right? Where theta is the parameter that determines the transmission and the reflection coefficient. So mod t is cos theta and mod r is sin theta. So this transformation can also be accomplished through the unitary transformation. So you define operator u, which is the exponential of the Hamiltonian, and then if this is u dagger, now A of theta and likewise so this is how the unitary transformation is carried out. So have you ever come across such transformations in your exposure to quantum mechanics, even in a rudimentary sense?
Yes, sir.
So you have come across these transformations, such expressions, right?
Yes, sir.
Okay. So u of theta is let me once again. Guess what it is? So why is this u of theta? You just substitute for h. Define a Hamiltonian of this form. Just plug this one here, you will get this expression. Okay, so okay, let us carry out the transformation for A. So the standard trick in quantum mechanics, quantum optics is to differentiate both sides with respect to theta. Okay, when you differentiate both sides with respect to theta, you get
Again, the signal has gone back.
what we're doing is you're differentiating both sides with respect to theta. So there are two terms that depend on theta, the exponent on the left and the exponent on the right. So a dagger b, a b dagger commutes with e to the power minus I theta a dagger b, a b dagger. That's why you can legitimately swap the order. So you get this term here, you write whatever you have here in the exponent times a times the second exponent, plus you use the product rule. Keeping the first term constant, we differentiate the second exponential term. That's what you get here. So is this clear so far, so good?
Yes, sir.
Okay, so now what we are going to do is now expand the terms in the curly brackets. Did I make? So I hope I have everything written down here. Okay, so now I'll start with this one. This has a positive I term, so let me just start with this one. I, A dagger, B, plus I, A, B dagger, minus I, A dagger, B, A. That can be written as A dagger, A, B, because B and A commute. Minus I, A, B dagger, A. Again we can write it as A, B dagger, because B dagger and A commute. Now these two cancel each other and you're left with, you can take I out. So is this step clear, whatever we have worked out so far?
Yes, sir.
Okay, so I can take I out because I is just a constant. Now I have now I can write this as A dagger B Now this is nothing but the commutator, and this is identity, correct? So which means you have but what is this one? U dagger of theta. This one is U of theta. So this is bay of theta. So we have, let me write a this is what we get. Okay. Now let us likewise calculate the transformation for bay of theta. So now let us say B so then we will have so I hope you are able to follow this. I am just replacing wherever we have A, I am just replacing that one by B. This one has to be worked out again. So now we will have, let us start from here. I B A dagger B is A dagger B B plus I A B B dagger minus I A dagger B B minus I A minus I A B dagger B. Yeah, these two will get cancelled. You can take I out. Now this is the commutator between B and B dagger, which is identity. So we have again Yeah, that's what you get. So that's clear. This is how you carry out the unitary transformation. So this is another way of computing the final result, carrying out the transformation for A and B. Okay. So what do we do now? This pair of equations should be familiar to you. So we had identical equations last time when we used Heisenberg's equation of motion to write down the evolution for A and B. So the standard trick is differentiate one of them with respect to, let us start with, take the first equation. Differentiate both sides with respect to theta. But what is dB by d theta? It's I times A theta. So which means and you know what is to be done. The general solution is alpha 1 so A of 0 is A, which is your input mode. So which is alpha 1, which is dA by d theta so IB of 0, which is IB, is alpha 2. So you have A of theta is so now to get B of theta, can do it here. I B of theta dA by d theta, which is minus A cos theta. Oh, I'm sorry. A sin theta which means so IA so you can write it in a more compact form. So I believe this is what we obtained last time as well. Okay, so this is a useful trick to know. So carrying out these transformations, you will come across such transformations repeatedly in quantum optics. Okay, so this is one of the standard tricks that you employ. So differentiate with respect to the parameter, convert that into a differential equation, and solve it. So is this one clear? Have you ever used this transformation at any point of time in your work, or come across this one?
You know, one means you are asking about quantum work or in general?
No, in general, whatever, in your exposure to quantum mechanics, not necessarily your research.
This transformation, we have seen, sir.
Okay, so you're familiar with the math, with the algebra.
Yes, sir. Yes, sir. Algebra is.
Okay, so this is what it is. So, all right. So now, let us discuss Hongo-Mandel effect. Of course, Hongo-Mandel effect is a bit subtle, so we will revisit Hongo-Mandel effect again and again in the future as well. So today will be the first round of discussion on Hongo-Mandel effect. Have you come across Hongo-Mandel effect in the past as part of your independent study?
Yes, sir. Yes, sir.
Okay, so have you also gone through the analysis in the single mode picture, like how the modes transform? Have you seen that?
Sir covered in last class.
Oh, okay. Oh, Professor Ghosh in his course last time. Okay. So we will discuss that once again today. So basically, it's pairs of single photons on a beam splitter. This is the Hongo-Mandel effect. So what is that? We consider two single photons with one photon incident on of the beam. What does it mean? This is our beam splitter. So one photon enters through mode through port A, and another photon through port B. So you have one photon in mode A, another photon in mode B. Okay, these are output modes, and we consider these two photons to be identical in every sense. They have the same wavelength, same polarization, all their internal degrees of freedom are the same. Okay, so they are indistinguishable. So psi n is this is same as 1a point B. So this is vacuum. Okay. And we assume that the beam splitter is 50-50. But we will, of course, we will impose the condition that the beam splitter is 50-50 a little later. So we have two single photons basically entering through two input ports of the beam splitter. Now 4 paths are possible for the two single photons, correct? So what path can the two photons take? How many possible outcomes are there for this particular configuration? So there are 4, right? So 4 elementary paths for two single photons. Paths for two single photons. On each input port of the beam splitter. Are possible. And what are they? We have one B. So what are the two possible paths? So first one is one can get transmitted. Okay, this photon from mode A gets transmitted, and this one gets reflected. Correct? So which means this is mode C and this is mode D. So which means how many photons will exit through mode D? For this particular possibility. So basically the A photon is transmitted, is reflected. So how many photons will exit through port D and how many will exit through port C?
Through port D 0, port C 2.
Right, exactly. So nothing exits through port D and both the photons emerge through port C, right? So this is one possibility. A second possibility, let us consider that A photon is reflected and B photon is transmitted. So what comes out of C? So A photon is reflected and B is transmitted. So what comes out of C?
Nothing.
Nothing. So vacuum here, and both the photons exit through port D. Now let us consider case 3. So case D, a photon is transmitted. B photon is also transmitted. So how many photons will exit through port C and D in this case?
One each.
One each. Good. So this is the third possibility. So case 4 is the A photon is reflected, likewise the B photon is also reflected. So now again, what will be the scenario in this case?
Again, one each.
One each, right? Good. So these are the 4 possibilities. So I was just trying to visualize them pictorially. So we have exhausted all the 4 possibilities, right? And there are no more possibilities. So now let us just do the math, work out the algebra, carry out the transformation explicitly, and see whether it's consistent with what we get here. Yeah. Okay, recall that from your notes that a dagger, if you want to write the input modes in terms of the output modes, this is how they are related. Okay. Now, once again, psi in is so all we have to do is to plug in for A dagger and B dagger in terms of C dagger and D dagger. So that will give us let me, yeah, I'm going to clean this part of it.
I think D dagger is having some issue.
It's having some issues, mean.
Because both the sides cause
So I'm sorry. This should be, no, you're right. This should be sine. Thank you so much. Yeah. Now it's consistent. Did I get, yes. Yeah, it's sine theta here. Now I think it's fixed.
Okay.
Yeah, thanks for pointing out the typo. it's so now we have the vacuum modes in C and D. Okay, now let us expand the terms in the bracket. This is what we have, plus cos square theta minus plus I square, that makes it minus 1, d dagger c dagger, that can be written as c dagger d dagger, sin square theta plus I d dagger square sin theta cos theta. That's what it is. Now I sin theta cos theta, c dagger, this is what it is, plus cos square theta minus sin square theta d plus I sin theta cos theta d dagger So what is this one? Square root of 2 times right. So 2 photons are created in mode C and nothing in mode D. One in mode C, one in mode D. One in mode C, one in mode D. Nothing in mode C, 2 in mode D. Okay. So this is psi out. So let me write down this expression on top, the final one. So what we get? I root 2 sin theta cos theta, 2 photons in mode C, nothing in mode D. So we can club. So to club this one and this one. And likewise cos square theta minus sin square theta, you can club these two because now this is what we get. Now from this picture here, can we identify the paths, like which term corresponds to which path? So which possibility to this term here, the first term, what possibility it corresponds to? We have 4 possibilities there. The first term,
Case 1.
this is 1. The second term, this one, which possibility?
Second case. Second case.
Yes, second case. Good. What about cos square theta 1c 1d? Which one is this? The third one. So this should be the fourth one. Now, why is there a minus sign? Why is it cos square theta minus sin square theta? So what does that minus sign correspond to?
Reflected signals are taking pi by 2 phase, so.
Very good. You're right, yes. So in the fourth possibility, both the photons get reflected. So each photon picks up a phase. You're right, pi by 2. Very good. So you get 2 factors of I. Right? So I squared is minus 1. So minus sign. As each reflection gives a factor I. Okay. So for a 50-50 beam splitter, theta is pi by 4. So which means sin pi by 4 cos pi by 4 is 1 over root 2, and is half. So in that case, in the case of a 50-50 beam splitter, these two terms cancel each other. So I'm left with sin theta is 1 over root 2, cos sin pi by 4 is 1 over root 2, cos pi by 4 is 1 over root 2. So you get I over root 2, because this root 2 will cancel one of them in the denominator. Oh, plus, I'm sorry. So this is the Hongo-Mandel effect. So what happens, you see that for a 50-50 beam splitter, both the photons either exit through port C or port D. You don't have the case where one photon exits through each port, C and D. Or what it means is, these two possibilities 3 and 4, they destructively interfere. The amplitudes destructively interfere, so you don't see that possibility at all. So when you send 2 single photons, pure single photons like Fox state through the two input ports of a beam splitter, then you will never detect any coincidence. If they reach the beam splitter at the same time without any delay, then you will see both the photons emerging through one of the output ports, either through port C or port D. Both the detectors will not click simultaneously. So this is one of the tests that you perform to verify the quantum nature of your source. So if you want to know whether you have produced pure single photons like Fox states, you look at the you study the Hongo-Mandel effect. Okay. So for a 50-50 beam splitter, these two possibilities 3 and 4 destructively interfere. So basically, if you actually do the experiment, so this is coincidence count on the delay. This one. So in the ideal case, theoretically speaking, there should not be any coincidence count, but in the lab there will always be some coincidence counts. The detector will, so those are probably the dark counts. So in an actual experiment, when the delay is 0, this corresponds to when I say delay, what I mean is that both the photons arrive at the same instant of time. They reach the beam splitter at the same instant of time. And when there is 0 delay, you will see a dip in the coincidence count. Okay? So that's the signature of Hongo-Mandel effect. This is the dip. And this is a signature of the Hongo-Mandel effect. So have you performed this experiment in your lab at any point of time? Or?
No, sir. We don't have a lab here to check here.
Okay. But you have seen this dip in the literature, right?
I understand, but practically also we have not seen.
So in the lab when you do it, the coincidence count will reach a minimum. So you should be able to, from the data, when you plot the coincidence count, when you plot the coincidence counts as a function of delay, you should be able to construct this curve. Okay, so that's the signature of Hongo-Mandel effect. So any question? Any questions so far, like either on Hongo-Mandel effect or on beam splitters?
No, sir.
So So it's already 310 or 311. So I don't think, so in this case, of course, the assumption was that both the photons are identical in every sense. They're identical in all their internal degrees of freedom, wavelength, polarization, so on and so forth. Okay. So next time we will see what happens when we send a pair of distinguishable photons through the two input ports of a beam splitter, and we will see it over the yeah.
So what is this coincidence to zero delay with that marking with arrows you have done in the graph?
Corresponds to.
Oh, it corresponds to zero delay. So this dip, you get this dip, the coincidence count goes to a minimum. You get the least number of coincidence count when both the photons, once again, here. So this is, so you send the photon, let us say this is your source, okay. Now the zero delay corresponds to the case where both the photons reach the beam splitter at the same instant of time. There won't be any delay. So it's not as if photon A reaches the beam splitter first and photon B reaches, say, 1 picosecond later, okay, or 5 picoseconds later. Both of them reach the beam splitter at the same instant of time. So that's what is meant by zero delay. So when if you keep increasing the delay, then the coincidence counts will increase, and beyond the point, if the delay exceeds the correlation time or the coherence time between the two photons, then you will get coincidences. So this will no longer be the state. Okay, that's what the delay tells you.
No, in the graph, where the dip is coming, that point corresponds to zero, and its axis is going plus and minus.
Yes, so it's positive and negative delay.
Okay.
So this will all be negative, positive. So that's what it is. And this negative and positive simply mean whether the photon leads or lags behind the other one. One leads or lags behind the other one.